everyone, welcome to part 2 of chapter 5. Last time we were talking about the mole, and the reason we use the mole in chemistry is because atoms are too small to count, right? We talked about it would be pretty ridiculous if I asked you to hand me 4 carbon atoms, right? Because they are so small, we don't measure individual atoms. We measure groups of atoms, specifically a mole of atoms, which we said was 6.022 times 10 to the 23rd atoms. And we can also use this for molecules, right? Because that word mole means a number, and that's called Avogadro's number. A little bit later, we also talked about the fact that we actually don't measure things out in moles in lab. Like if you think about being in lab, we measure amounts of substances in grams, right? We'll go and we'll take our substance and we'll put it on the balance and it'll give us a mass in grams. So we needed a way to relate that grams to a number of atoms. So we said that the way that we do that is that we use the mass on the periodic table. And that mass on the periodic table is the mass of 1 mole of any element. So last time we learned 2 different conversion factors. The molar mass is equal to 1 mole, and Avogadro's number is equal to 1 mole. And we learned how to do some one-step conversions using those 2 different equalities. Today, we're going to learn how to put them all together and learn about the information we can get from chemical formulas. So lots to cover today. Let's get going. So here's an example problem. This says how many gold atoms are contained in 16 grams of gold. So if you can imagine us doing this in lab, we go to the back of the room and we use the balance and we measure out 16 grams of gold. And I want to know how many atoms are in there. Well, last time we learned that we can convert grams to moles using the molar mass, right? And so specifically for gold here, that would be 1 mole is equal to 197.0 grams of gold. And remember, we're getting this number from the periodic table. So if you don't have your periodic table handy right now, I would go and grab it along with a calculator, your pencil, and the chapter 5 lecture worksheet, because all of those will be super helpful for you in today's lecture. All right. Once we convert our grams of gold to moles of gold, then we can use Avogadro's number, and we can get from moles of gold to atoms of gold. So that'll be this conversion here. All right, so let's go ahead and see how we do this. Last time, we used only one-step conversions, right? We were just using one equality. But we've done these 2-step conversions before when we were working on just learning about the metric system, and this is going to work the same way. We're going to convert grams to moles in one step and then moles to atoms in another step. So just like any other problem, we have to figure out what we're starting with. And so here we're starting with 16 grams of gold. So that will go in the beginning of my train track here. We know grams of gold has to cancel grams of gold. So the only conversion that we know that uses grams is this one here. So 197 grams of gold has to go on the bottom in order to make sure that those units cancel. Remember, when things are equal, they get stacked. So if this side goes on the bottom, that means this side has to go on the top. So we'll make sure our units cancel. That's how we know we're doing it right. And then we see, have we found what we're actually looking for? In this case, we are looking for atoms of gold. And right now, we've only found moles. So we need to keep going. The way we convert from moles of gold to atoms of gold is we use this, right? That was Avogadro's number. We learned that last time. Remember, moles of gold has to cancel moles of gold. So that means that 1 mole of gold will go on the bottom here, and 6.022 times 10 to the 23rd atoms of gold will go on the top. We'll make sure our units cancel, and then check and see we found what we were actually trying to find. So we were trying to solve for atoms of gold, and that's what we've got here. So that's how we know that we're done. Now we're going to multiply all of the numbers on the top and divide by all the numbers on the bottom, and we get our answer. Remember, just like we talked about last time, you always need to have a number, a unit, and a chemical in your answers and in every box of the train track to make sure that your units are canceling correctly. This will be really important when we get to a later chapter on stoichiometry because we'll actually change chemicals along the way. We're going to change a little bit of our substances today, so again, make sure you're labeling everything correctly. Alrighty, I want you to go ahead and do this practice problem. This says how many titanium atoms are contained in 7.80 grams of titanium. Okay, so this is very similar to our last problem, except we're using titanium instead of gold. Go ahead, pause here, try this out, and come back when you're ready to see the answer. Alrighty, so what we're going to do here is we're going to make a two-step train track. We're going to turn grams of titanium into moles of titanium, and that we will use the molar mass, and then we'll change moles of titanium into atoms of titanium, and for that, we'll use Avogadro's number. Okay, so those are our two equalities here. We need to use 1 mole equals the molar mass to change from grams to moles, and then we'll use Avogadro's number to change from moles to atoms. So let's go ahead, we'll start our train track with this. Remember, grams of titanium has to cancel grams of titanium. So if I have grams of titanium there, then I have to have grams of titanium down here. So that means that 47.87 grams of titanium will go on the bottom to make sure our units cancel. Remember, when things are equal, they get stacked. So if this side of our equality goes on the bottom, then that means that this side has to go on the top. Okay, so we make sure our units cancel, and then we look to see, did we find what we were looking for? We're looking for titanium atoms, and right now we've solved for moles of titanium, so we have to keep going. The way that we get from moles to atoms is we use Avogadro's number. That 1 mole equals the 6.022 times 10 to the 23rd atoms. Remember, moles of titanium has to cancel moles of titanium. So this portion of our equality will go on the bottom, and 6.022 times 10 to the 23rd atoms will go on the top. Make sure your units cancel so you know you're setting it up right, and then you'll get your answer. Again, make sure your answer is rounded to the correct number of significant figures and has a number, a unit, and a chemical. Let's try this one. Okay, this says, what is the mass of 1.28 times 10 to the 24th atoms of neon? So this problem is a little bit different. Before, we'd been starting with grams and solving for atoms. In this one, we're starting with atoms and we're trying to figure out grams, right? Remember, mass is measured in grams. So I want you to try this one. Write down the equalities that you know, just like we've done on the previous two problems, and see if you can set up your train track to give you grams at the end. So go ahead, pause here, try that out, but when you're ready to come back and see the answer, unpause and we'll go through it. Alrighty, so here's our game plan. We're going to turn atoms of neon into moles of neon, and we can do that by using Avogadro's number. And then we can change moles of neon into grams of neon using the molar mass. So this is kind of like what we did in the last problem, except almost completely backwards. So let's see how we set that up. So we go ahead, we figure out what are we starting with. So that's here. We're starting with 1.28 times 10 to the 24th atoms of neon. So that will go in the beginning of my train track. The first thing we need to do is convert atoms to moles, and we do that using Avogadro's number. So remember, our units have to cancel. If I have atoms of neon here, then I need to have atoms of neon down here, which means that this portion of our equality will go on the bottom, and 1 mole will go on the top. Because remember, when things are equal, they get stacked. All right, we make sure our units cancel, and now we've solved for moles of neon. But that's not what we're trying to find. Remember, we're trying to find mass, which is in grams, so we have to keep going. Now we can use the molar mass to change moles of neon into grams of neon. So that's what we've got up here. Remember, our units have to cancel, so if we have moles of neon here, we have to have moles of neon down here. So that means that 1 mole of neon will go on the bottom, and that 20.18 grams of neon will go on the top. Make sure our units cancel, and then multiply everything out, and we'll get our answer. All right, so thus far we've been doing this with elements, but we can actually do this with compounds as well. So in order to do this whole process for compounds, we need to figure out the mass of a compound, and it's actually a pretty straightforward and logical process. Okay, so we're still going to call it the molar mass. This is the mass of 1 mole of our compound, or our molecule. So the molar mass of a compound is equal to the sum of the molar masses of all of the atoms in the molecule. Essentially, what this means is we're going to look at the chemical formula of our substance and just add up the masses of everything that's in it. So for example, H2O. We have 2 hydrogens and 1 oxygen. So we're going to add up the masses of 2 hydrogens and 1 oxygen. I think it's pretty logical, but this is how I have it set up. So we know there's 2 moles of hydrogen and 1 mole of oxygen based on the subscripts. So 2 moles of hydrogen, and remember this is an imaginary 1, so 1 mole of oxygen. So that's where I'm getting these numbers. So now we're going to take those subscripts, right, the 2 and the 1, and we're going to multiply it by the mass. So on the periodic table, hydrogen is 1.008, so we're going to multiply 2 times 1.008 to give us the mass of 2 hydrogens. And then we'll multiply 1 times 16 because there's 1 oxygen. So that's here. This is the total mass of hydrogen and the total mass of oxygen. If we add those up, then we get the molar mass of water, 18.02 grams. Just so you know, we'll use water a lot in this class, and it's likely you'll accidentally memorize this molar mass, but you never have to memorize masses in this class. Okay, you'll always have a periodic table available to you. All right, let's try this out. What is the molar mass of aluminum hydroxide? So I've written out the chemical formula there right now, but we've already done nomenclature in this class. So it's very, very possible that I would just give you the words aluminum hydroxide and you would have to figure out this chemical formula and then find the molar mass. So just because we've passed the chapter on nomenclature doesn't mean you can forget it all. We're going to use it very frequently as we move forward in this course. So just keep that in mind and keep practicing your nomenclature. All right, I want you to pause here and try to figure out the molar mass of aluminum hydroxide just like we did for water on the previous slide. So pause here, try that out, and then come back when you're ready to see the answer. Alrighty, so going through this, if we look at aluminum hydroxide, we have 1 aluminum, and then this 3 actually gets distributed in. We end up having 3 oxygens and 3 hydrogens. Okay, this is just like math class, right? Where we have numbers outside parentheses and they distribute in. Same thing happening here. That 3 distributes into everything that's inside the parentheses. So we have 1 aluminum, 3 oxygens, and 3 hydrogens. So we take those coefficients, right? The 1, the 3, and the 3, and we multiply it by the mass of each of the elements. So 1 times 26.98 for aluminum, 3 times 16 for oxygen, and 3 times 1.008 for hydrogen. Once we get all of these masses, right, so this is the mass of aluminum and then oxygen and hydrogen, we'll add all of those up to get the molar mass of that compound. So the molar mass of aluminum hydroxide is 78.00. So just like we were using the molar mass as a conversion factor for elements, we can also use the molar mass as a conversion factor in these calculations for molecules and compounds. So for example, we found the molar mass of water was 18.02 grams. So we can use this equality here, 1 mole of water is equal to 18.02 grams because that's the molar mass of water. So we can use this in our train tracks just like we've done with all of our other equalities. We can put our mass on top of moles or our moles on top of mass. It'll just depend on how we need to use it in our train tracks to make sure things cancel. All right, let's go through this. So this problem says, how many moles of sodium chloride are there in 253 grams of sodium chloride? So we're going to start with 253 grams of sodium chloride in the beginning of our train track, just like that, okay? But whenever we're starting with grams, we are going to need to find the molar mass in order to convert between grams and moles, right? Because if you'll recall, that's how we were doing that conversion, right? The way to get from grams to moles is to use the molar mass of an element, or in this case, the molar mass of a compound. So to find the molar mass of sodium chloride, we do just what we were doing before. So in this chemical formula, we have 1 sodium and 1 chlorine. So that's where we're getting these 1s here. So we'll do 1 times each of their masses, 22.99 for sodium, 35.45 for chlorine, and then we add them up. and that gives us the molar mass of sodium chloride. So 58.44 grams of sodium chloride is equal to 1 mole of sodium chloride. Okay, so that's an equality we can use in our train tracks. So if I'm starting with 253 grams of sodium chloride, remember our units have to cancel down and to the right. So if I have grams here, I have to put grams here, which means that 58.44 grams of sodium chloride is going to go on the bottom, and then 1 mole of sodium chloride will go on the top. Make sure our units cancel and see if we found what we're trying to find. In this particular case, I was looking for moles of sodium chloride, and I found moles of sodium chloride. So I stop. In this case, we don't need to convert to atoms or molecules because the problem just asked us to go to moles. So make sure you're looking out for that and you're not doing too many steps if you don't need to. All right, so now we have this all set up. We'll multiply the top, divide the bottom, and we'll get our answer. All right, I want you to try this out. So this says, what is the mass of 3.45 moles of lithium oxide? Okay, so notice here that you're converting between moles and mass. So that means you're going to need to find the molar mass of lithium oxide and use that in a conversion factor for solving this problem. Okay, so go ahead, pause here, try that out, and come back when you're ready to see the answer. Alrighty, so in this case, like I said, we're going to need to use that molar mass to convert between grams and moles. So let's go ahead and calculate the molar mass. So here we have 2 moles of lithium and imaginary 1 moles of oxygen. So we do 2 times lithium's mass and 1 times oxygen's mass, and then we'll get those and then add them up and get the molar mass of lithium oxide. So remember, that mass is equal to 1 mole of lithium oxide, so we can use that equality as a conversion factor in our train tracks. So we're starting with 3.45 moles of lithium oxide, so we'll put that there. Remember, our units have to cancel, so if I have moles of lithium oxide here, I need to have moles of lithium oxide down here, which means this portion of our equality is going on the bottom, and the grams will go on the top. So this is different than our previous problem, right, where we had grams on the bottom. Remember, the way you're going to know which one goes on the top or bottom is to make sure your units cancel. The reason that it went on the bottom, right, 1 mole went on the bottom here, is that moles had to cancel moles. And in the previous problem, we started with grams, so that's why this was flipped upside down. So just keep an eye on that when you're trying to set up these train tracks. Now let's figure out if we finished solving our problem, right? We're looking for mass, and remember, we measure mass in grams, and we found grams of lithium oxide. So that means we're done with this problem. We can multiply the top, divide the bottom, and get our answer. Alrighty, go ahead and pause here and complete problems number 15 to 21 on the Chapter 5 lecture worksheet. This will get you some work on converting from grams to moles to molecules or vice versa, and it will also help you practice calculating the molar mass. Once you're done, come back and we'll keep going. Alrighty, so we've learned how to convert from grams to moles and moles to molecules for both atoms and molecules and compounds and all of that good stuff, right? Now we can do 2 conversion steps, which is awesome. Sometimes, though, we need different pieces of information. We might want to know how many individual carbon atoms there are, or how many individual hydrogens there are in a molecule, right? And so we can actually get a lot of this information from our chemical formula. These subscripts are really important. Okay, so take, for example, aspirin. Aspirin is C9H8O4, and this is its chemical structure if we were to build it using model kits. Kind of cool. So if we look at this chemical structure and you were to, count up all of the carbons are the black ones. There are 9 carbons, which you can see here. There are 8 hydrogens, and there are 4 oxygens. So if I just took one molecule, like it's shown here, and I just took it all apart. I took all of those little bonds apart like these are, connects or something like that, right? I took this all apart. I would sit here with 9 individual black balls that represent carbon. I would have 8 individual white balls that represent hydrogen and 4 individual red balls that represent oxygen. So in 1 molecule of aspirin, I'm getting 9 carbon atoms, 8 hydrogen atoms, and 4 oxygen atoms. And like I said, that's just by taking it apart. So this is important on, a small level, right, on a molecular level, but more importantly, for us anyways, is the macro scale, right, the moles of each element. So let's say instead of having 1 individual molecule of aspirin, let's say I have a mole of aspirin, because that's an amount that I can actually weigh out in lab. So if I have a mole of aspirin, that means I have 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. So these subscripts here are telling us the ratio of how many atoms there are in that molecule if I take it all apart, but it's also telling us the ratio of moles to moles. Again, if I took apart a mole of aspirin molecules, that means I would end up with 9 moles, 9 moles of carbon atoms, 8 moles of hydrogen atoms, and 4 moles of oxygen atoms. So we call these mole ratios because we can use the subscripts to tell us how many individual atoms are contained in that molecule. So here's how it can be used as a conversion factor, right? So the subscripts, this is aspirin again, can be used to solve a problem like the one shown below. So it says how many moles of carbon are present in 1.50 moles of aspirin. So now do you see we're actually changing substances. We're changing from moles of aspirin to moles of carbon. So this is why it's really important to label the number, the chemical, and the substance whenever you're doing train tracks or writing down your answer, because the substances can change. All right, so here's our equality that we know to relate these two pieces of information. In 1 mole of aspirin, there's 9 moles of carbon, and I'm getting that 9 from right here. There's 9 moles of carbon. Okay, so anytime we can write an equality like this, that means we can use it as a conversion factor. We could put 9 moles of carbon on the top and 1 mole of aspirin on the bottom, or 1 mole of aspirin on the top and 9 moles of carbon on the bottom. It really just depends on how we need to set up our train track. So let's solve this just like we have any other problem. We have to go and figure out what we're starting with. So here we're starting with 1.50 moles of aspirin. So that's what I've got here. We're trying to find moles of carbon. So this is our equality we're going to use. Remember, moles of aspirin has to cancel moles of aspirin. So this part is going to go on the bottom, and our 9 moles of carbon will go on the top. Okay, so be careful here. If you hadn't written the number, the unit, and the chemical, and say you just wrote the number and the unit, you wouldn't know how many moles of what, right? And we wouldn't know whether we would, put moles of aspirin on the bottom or moles of carbon on the bottom. Since this is moles of aspirin, we knew we had to put moles of aspirin down here. So just be very, very careful with your labeling so that you don't get mixed up. All right, so we can make sure our units cancel and see if we found what we're trying to find. We were trying to find moles of carbon, and we found moles of carbon. So that's how we know we're done. We'll multiply all of the numbers on the top, divide by numbers on the bottom, and we'll get our answer. All right, I want you to try one. How many moles of hydrogen are present in 3.50 moles of nitrogen trihydride? So you'll notice here, I haven't given you the chemical formula, right? Remember, we did that whole chapter on nomenclature. So you should know how to write the formula of nitrogen trihydride. If you don't, I would recommend going back and looking at your notes and seeing if you can figure it out, because it's very, very important to know how to do this. All right, go ahead and pause here, solve this problem, and come back when you're ready to see the answer. All right, so the first order of business is to figure out what nitrogen trihydride is, right? If you look at this and find your periodic table, nitrogen is a nonmetal and hydrogen is a nonmetal. So remember, when we have 2 nonmetals, That's molecular bonding, okay? And that means we're going to use the prefixes to tell us how many of each substance there are. You also may have noticed this prefix here, right? Anytime you see a prefix, remember that that's molecular bonding, and you're just going to use prefixes to tell you how many of each element you have. So there's nothing in front of nitrogen, so that means there's just one. And tri means 3, which is telling us that there's 3 hydrogens. So 1 nitrogen and 3 hydrogens. So that's what I have written there. So from this chemical formula, we can see that 1 mole of nitrogen will give us 3 moles of hydrogen, because remember, that's 3 here. So 3 moles of hydrogen. Okay, so we can start our train track with our 3 moles of nitrogen trihydride, which is what it says right here, 3 moles of nitrogen trihydride. So that goes in the beginning of our train track. Now we can use this equality as a conversion factor to convert between moles of nitrogen trihydride and moles of hydrogen. Remember, your units have to cancel down and to the right. So if I have moles of nitrogen trihydride here, then I need to have moles of nitrogen trihydride down there. So that 1 mole will go on the bottom and 3 moles of hydrogen will go on the top. We'll make sure our units cancel so that we know we've set it up correctly, and then we see, did we find what we were looking for? Here we have 3 moles of hydrogen, right? And we were looking for moles of hydrogen. So that's how we know we're done making our train track. Now we can go ahead and multiply the numbers on the top, divide by numbers on the bottom, and we'll get our answer. All right, let's make this a little bit trickier. This one says how many hydrogen atoms are in 1 mole of hydrogen gas. Okay, so this wants to know how many individual hydrogen atoms are in 1 mole of H2. You'll notice that this says H2, and the reason it says H2 is because hydrogen is a diatomic molecule. So anytime you have hydrogen by itself, it actually exists as H2. Remember, the way we remember diatomic molecules is Hofbrinkel. And that's going to be really important as we move forward in this course. All right, so let's set this up. We start with 1 mole of hydrogen in the beginning of our train track. Okay. In order to convert to individual hydrogen atoms from moles, first we need to figure out how many molecules there are. Okay. We know how to go from moles to molecules because we've been doing that earlier, right? Going from moles to molecules, we are going to use Avogadro's number. That's how we get essentially from the macro scale to the micro scale. Get from moles of a substance to atoms or molecules of a substance. And my apology, this should say molecules of H2. My apologies there. All right, so we can go ahead and convert 1 mole of H2 on the bottom and Avogadro's number of molecules of hydrogen on the top. Okay, so we see that our units are going to cancel and we get molecules of H2 on the top. But it doesn't want molecules of H2. Our problem wants hydrogen atoms, so individual hydrogen atoms. This H2 means 2 hydrogens that are bonded together. So essentially, this problem wants us to break those that bond apart and tell us how many individual hydrogens I have. So we can do this just like we've been doing before. 1 molecule of H2 will give us 2 individual atoms of hydrogen. So we'll put 1 molecule of H2 on the bottom and that 2 individual atoms of hydrogen on the top. We can cancel out our units and then we'll get our answer. All right, you go ahead and try one. This is very similar to the last problem, except now we're doing it with sulfur. So this problem says if we have 2.27 moles of S8 molecules, how many individual sulfur atoms do we have? So go ahead, pause here, write your equalities, and see if you can figure this out. And then come back when you're ready to see the answer. All right, so our game plan, just like we did last time, is to take moles of sulfur and convert it into molecules of S8. And then once we get our molecules, we can break that molecule apart into individual atoms, and for that, we need the subscript. So to get from moles to molecules, we say, okay, 1 mole is equal to Avogadro's number. Again, that's how we're getting from, a lot of stuff to individual atoms or molecules. And then we can use 1 molecule of S8 to convert to individual atoms of sulfur. So we'll start our train track with our 2.27 moles of S8. Okay, then we'll use Avogadro's number to convert from moles to molecules. Remember, make sure your units cancel. So your units need to cancel down and to the right. So moles of S8 has to cancel moles of S8. Once we finish that, we look and we see, did we find what we were looking for? We were looking for sulfur atoms, and right now we've solved for molecules of S8. So we have to keep going. We know that for every 1 molecule of S8, there are 8 individual atoms of sulfur if I take this whole thing apart. So 1 molecule of S8 will go on the bottom, and our 8 atoms of sulfur will go on the top. We'll make sure all of our units cancel, and then we'll get our answer. All right, let's try another one. This says, how many atoms of hydrogen are present in 7.53 grams of dihydrogen sulfide, or hydrosulfuric acid? Okay, this problem is different than the previous one because now we're starting with grams. Okay, before we were starting with moles, right? And we converted moles to molecules and then molecules to individual atoms. But now we're starting with grams, so this makes the problem even longer. Now we need to convert grams to moles, and then we can pick up kind of where we were doing last time. We can convert moles to molecules, and then molecules to atoms. So this is going to be 3 different conversions. The first thing we need to do, though, is to get from grams to moles. The only way we know how to convert from grams to moles is to use the molar mass. So we'll go ahead and we'll find the molar mass of H2S. So we'll do 2 times the mass of hydrogen, 1 times the mass of sulfur, and then add up those values to get the molar mass of H2S. Remember, that is going to equal 1 mole of H2S, which is why it's called the molar mass. All right, so now let's go ahead and set this train track up. So we're starting with our 7.53 grams of H2S. We'll use that molar mass to convert from grams to moles. Remember, our units have to cancel, so if we have grams here, we have to have grams down here. So make sure our units cancel, and then we'll see where we're at. Now we've got to moles, and we need to convert to molecules. The way we convert to molecules is to use Avogadro's number. So we'll use 1 mole of H2S is equal to 6.022 times 10 to the 23rd atoms. Oops, sorry, not atoms, molecules, my apologies, molecules of H2S. And just so you know, the reason we know that this is the word molecules and not atoms is because this is a compound. Okay, that's more than 1 element. So that's why we use the word molecules. If it was a single element, we would use the word atoms. Okay, so now we have our equality up there. Remember, moles of H2S has to cancel moles of H2S, so 1 mole will go on the bottom, and our number of molecules will go on the top. We'll make sure our units cancel, and then double check what we're looking for. We're looking for atoms of hydrogen. So we're not done yet. We have to keep going because right now we have molecules of H2S. So if you look, for every 1 molecule of H2S, do you see that we have 2 atoms of hydrogen here? So for every 1 molecule of H2S, we have 2 atoms of hydrogen. We make sure our units cancel, and then we make sure, okay, did we find what we were looking for? We were looking for atoms of hydrogen, and we found atoms of hydrogen. So we can now go ahead and multiply all of the numbers on the top and divide by all of the numbers on the bottom, and we'll get our answer. This was a long one, right? This had 3 different conversion factors that we needed to use. So make sure you're understanding when you use each conversion. Anytime you're trying to get between grams and moles, you'll use the molar mass. Anytime you're trying to get between moles and molecules or moles and atoms, you'll use Avogadro's number. And if you're trying to get between molecules and atoms, then you'll use that mole ratio from the chemical formula. Okay, so that's really important to try and know where you're going, where you started, right? All of that. And what conversion factors do you have available to you to help you get there? All right, I want you to try this one out. So this is very similar to the last problem that we did. So use that as your guide. Here, this one says, how many atoms of hydrogen are there in 0.759 grams of hydrogen peroxide? Go ahead, pause here, try this out, and then come back when you're ready to see the answer. All right, so we're trying to convert grams of hydrogen peroxide into atoms of hydrogen peroxide. The only conversion factor we know with grams is to turn grams into moles using the molar mass. So let's go ahead and start there. So in order to turn grams into moles using the molar mass, we need to find the molar mass. So the way we do that, we'll do 2 times the mass of hydrogen, 2 times the mass of oxygen, and then we'll add those up to get the molar mass of hydrogen peroxide. And remember, that's equal to 1 mole of hydrogen peroxide. So we can use that as a conversion factor to convert between grams and moles. All right, so let's set up our train track. So we're starting with 0.759 grams of hydrogen peroxide. So that goes in the beginning of my train track. Remember, our units cancel down and to the right, so grams of hydrogen peroxide has to cancel grams of hydrogen peroxide. So our molar mass will go on the bottom, and 1 mole will go on the top. Okay, we'll make sure our units cancel, and then see where we're at. Right now, we have moles of hydrogen peroxide, and we're trying to solve for atoms of hydrogen. So we're going to need to convert first between moles and molecules. We know that for every 1 mole of hydrogen peroxide, there are 6.022 times 10 to the 23rd molecules of hydrogen peroxide. So we can use that as a conversion factor. Remember, our units have to cancel down and to the right. So 1 mole of hydrogen peroxide will have to cancel with 1 mole of hydrogen peroxide. And then Avogadro's number will go on the top. We'll make sure our units cancel, and then we'll see where we're at. So right now we have moles of hydrogen peroxide, and we're trying to find atoms of hydrogen. So we're not done yet, we have to keep going. The way we get from molecules to atoms is to use that mole ratio. So we say, okay, for every 1 molecule of hydrogen peroxide, we need to figure out how many atoms of hydrogen there are. Well, there are 2 atoms of hydrogen. So that's our last conversion factor. So for every 1 molecule of hydrogen peroxide, there are 2 atoms of hydrogen. Make sure your units are canceling down and to the right, and that you found what you were looking for. We were looking for atoms of hydrogen, and that's what we're ending up with. So now we can multiply all the numbers on the top, divide by the numbers on the bottom, and we'll get our answer. Alrighty, that actually concludes our lecture for today. We covered quite a bit of ground, and we learned how to do longer conversions, right? With more steps in the middle. We learned how to convert all the way from grams to molecules or grams to atoms or vice versa, right? In those 2-step conversions. We also learned how to calculate the molar mass of a compound and use that in our train tracks to convert between atoms and molecules of a compound and grams, right? Because it's really important. And then finally, we learned how to use the subscripts in our compound as a conversion factor as well to convert from molecules of a substance to atoms of one of those individual elements that are making up that compound. Okay, so we learned a lot today. This is a very math-based chapter. So do make sure you're doing all of the recommended lecture worksheet problems to get in adequate practice to be really good at the math portion. A lot of people, when they start off with Chem 20, say that they're nervous about the math in this class. I will tell you now, if you do the recommended practice problems on these lecture worksheets, you will feel confident in doing the math in this class. So make sure you're doing them and always check your work against the answer key to make sure you're doing every part of it correctly. Make sure your setups look just like mine and that you're showing the number, the unit, and the chemical and canceling out your units so you know you're doing the right thing. Also make sure you're plugging things in the calculator correctly and that that's not what's tripping you up. As always, if you have any questions at all, whether it's about the content or your calculator or anything else in the class, please send those questions my way. I am more than happy to help you out, and I like answering questions. Otherwise, keep working hard and do a lot of practice problems. Otherwise, I'll talk to you guys next time.